Hi team, and welcome to the first screencast for Chapter 20. Chapter 20 is all about water pollution. In this screencast, we'll cover sections 20-1 and 20-2. This chapter begins with a discussion of dead zones in the Gulf of Mexico. These dead zones are caused by huge inputs of nutrients from the Mississippi River Basin, from fertilizers from agricultural operations in the spring and summer. This huge input of nutrients causes an algae bloom, followed by an algae die-off, and then a depletion of oxygen in the bottom layer of water. Dead zones contain little marine life due to the lack of oxygen. Dead zones are initiated by disruptions to the nitrogen cycle, such as excess nitrogenous fertilizers in the water. The two maps on this slide show the extent of dead zones in the Gulf of Mexico in 2011 and 2014. This map shows the Mississippi River Basin, or watershed. Any agricultural runoff in this area makes its way to the end of the Mississippi River into the Gulf of Mexico. This satellite map shows where the Mississippi River empties into the Gulf of Mexico. It also shows an algae bloom taking place. These algae blooms can lead to the formation of dead zones. In section 20-1, we'll talk about the causes and effects of water pollution. Water pollution is defined as a change in water quality that can harm organisms or make water unfit for human uses. Water pollution can come from one of two different types of sources. There are point sources of water pollution, which are located at specific places. You can point to where the water pollution is coming from. Point sources of water pollution are easy to identify, monitor, and regulate. The discharge pipe shown here on the right is an example of a point source of water pollution. The image on the left shows an interesting statistic. Textile dyeing and treatment is responsible for about 17 to 20% of total global industrial water pollution. Water pollution can also come from non-point sources. These are broad, diffuse areas that can produce pollutants that lower water quality. Non-point sources of pollution are difficult to identify and control, and the pollution that they create is expensive to clean up. The diagram on the left shows different non-point sources of water pollution, including city streets, suburban development, croplands, and animal feedlots. You should be familiar with the three leading causes of water pollution. First, there are agricultural activities that produce eroded sediment, fertilizers, and pesticides. Second, there are industrial facilities. Factories and processing plants can produce and release inorganic and organic chemicals. Third, there's mining. Mining can cause erosion, expose toxic metals, and produce toxic chemicals through processes like acid mine drainage. This example of water pollution is from a factory in Gargas, France. Soil erosion on farmland can create sediment pollution. The sediment can change the course of streams or clog them up. Water can also be polluted with infectious disease organisms or pathogens. Contaminated drinking water is responsible for about 1.6 million deaths around the world each year, mostly involving children. Cholera, giardiasis, and typhoid fever are all examples of diseases caused or spread by contaminated drinking water. These images show the symptoms associated with cholera caused by a bacterium on the top left, the symptoms associated with typhoid fever on the right, and the parasite that causes giardiasis, called Giardia, on the bottom left. This table summarizes major water pollutants and their sources. It's broken down by type or effect, examples, and major sources. Note that heat can cause a type of pollution called thermal pollution, especially in areas around power and industrial plants. Factories and power plants use water mainly for cooling. When they discharge this water back to where they got it from, this water can be 10 to 15 degrees Celsius higher. This excess heat, again, is called thermal pollution, and warmer water holds less oxygen and can speed up fish metabolism, affecting ecosystems in surrounding areas. For the remainder of this section, we'll look at different ways in which we can monitor water pollution and water quality. First, we can look at conductivity. Conductivity is a measure of water's capability to pass electrical flow. This is usually caused by ions like salts. Pollutants can increase conductivity. For example, a freshwater stream will normally give a conductivity reading somewhere between 100 and 2000 microsiemens per centimeter. Industrial wastewater, however, will give a conductivity reading around 10,000 microsiemens per centimeter. Dissolved oxygen concentration is the amount of oxygen found in water. Moving water tends to contain more oxygen than standing water. Also, aerobic bacteria consume oxygen when decomposing organic matter. This is what leads to dead zones, one of which is shown here on the left. We can also look for the presence or concentration of plant nutrients. Plant fertilizers tend to be high in nitrates and phosphates. These can initiate the algal blooms that can cause dead zones. We can also do bacterial counts. Fecal coliform test for bacteria that originate in the intestines of warm-blooded animals. Fecal coliform tests are effective to see if your water is contaminated with infectious disease organisms. Looking at sediment load gives you an idea of the pollution produced by erosion. Erosion increases the turbidity or cloudiness of the water that you're looking at. In section 20-2, we'll look at the major water pollution problems in streams and lakes. Streams can cleanse themselves of water pollution as long as we don't overload them. Water can dilute pollutants, and bacteria can biodegrade pollutants. Bacteria, however, can also deplete oxygen as they do this. This creates what we call the oxygen sag curve, areas of lower dissolved oxygen where water pollution is present. The oxygen sag curve is created by changes in biochemical or biological oxygen demand, BOD. This is the dissolved oxygen required by aerobic bacteria to break down organic material. Increased pollution will increase biochemical or biological oxygen demand and therefore decrease dissolved oxygen concentrations. The oxygen sag curve is visualized here on the left. More developed countries have found ways to deal with and control water pollution. In the 1970s, water pollution control laws led to successful water cleanup stories, such as the Cuyahoga River, shown burning here on the left in Ohio, and the Thames River, shown here on the right in Great Britain. These countries have found ways to deal with contamination of water by toxic, inorganic, and organic chemicals by industries and mines. The picture is different in less developed countries. Half of the world's 500 major rivers are polluted. In less developed countries, they're polluted with untreated sewage and industrial waste. Unfortunately, this is the same water used for human activities. This is a photo of China's Yangtze River. It's polluted with chemicals, sediment, and trash. Lakes are less effective at diluting pollutants than streams are. This is due to a number of reasons. There's little vertical mixing up and down in a lake. There's little or no water flow into or out of a lake. And biological magnification can lead to increases in pollutants in organisms and in the lake when the organisms die and decompose. Lakes that are low in nutrients, high in dissolved oxygen, and are clear are called oligotrophic lakes. Nutrients can build up in these lakes over time in a process called eutrophication. Some eutrophication is good because it allows plants to grow and ecosystems to become established and more complex. Too much eutrophication can be a bad thing. When there are excess nutrients in the water, this can cause an algae bloom, followed by an algae die-off. Bacteria will break down and decompose the dead algae, depleting oxygen from the water and creating a dead zone. Cultural eutrophication refers to eutrophication caused by human activities. These activities lead to excess levels of nitrates and phosphates in the water. Fertilizer, feedlots, sewage, urban runoff, and mining all contribute to cultural eutrophication. As mentioned before, the excess nutrients can cause algal blooms. This usually happens during hot weather and droughts when the water can't be diluted. As the algae die off, aerobic bacteria decompose the algae and deplete oxygen from the water. After that, anaerobic bacteria take over. These anaerobic bacteria can produce smelly hydrogen sulfide and methane. This is a photo of an algae bloom in Chaohu Lake in China. We can prevent or reduce cultural eutrophication by removing nitrates and phosphates from wastewater. We can also divert wastewater from lakes and other standing bodies of water. We can also clean up lakes, but this is expensive. We can use herbicides and algicides to prevent algae blooms. And we can also pump in air to prevent the formation of dead zones. San Francisco has 3 water treatment facilities: the Oceanside Treatment Plant, the Southeast Treatment Plant, and the North Point Wet Weather Facility. These water treatment facilities reduce nitrate and phosphate levels in wastewater and slow down cultural eutrophication. This photo shows a boat that removes algae from Oakland's Lake Merritt. The dead zones in the Gulf of Mexico are an extreme case of cultural eutrophication. Nitrate levels in the Mississippi River have nearly tripled since 1950. This has caused blue-green algae blooms in the Gulf of Mexico. Flood control measures in the form of levees and dikes have sped up the flow of water in the Mississippi River. This has led to increased erosion in the river and sediment pollution in the Gulf. The increased nitrates and flood control measures have led to the dead zones and subsequent fish kills. In 1972, the governments of Canada and the United States initiated a program to control water pollution in the Great Lakes. This program resulted in decreased algal blooms and increased fish catches. The map on the left shows the Great Lakes and their drainage basins. The satellite images on the right show the development of an algal bloom in Lake Erie. The water pollution control program for the Great Lakes included better sewage treatment plants, fewer industrial waste, and bans on phosphate-containing household products. Despite the success of the program, there are continuing problems. Urban sprawl and runoff continue to contribute pollutants to the water. Biological pollution in the form of invasive species like zebra mussels continue to cause problems for people and native organisms. And finally, atmospheric deposition of pesticides and mercury continue to plague the area.